Jai Hind all of you. In myself Mani Dwivedi from AKGEC Ghaziabad. In my lecture series of software engineering, today I am going to start with a new topic, that is functional testing. In this series, I am going to cover the following contents like classification of testing and the functional testing, in which the two subtopics are there: boundary value analysis and the equivalence class partitioning. Before going into the detail of classification and the functional testing, let us discuss what is software testing. I will say the software testing is the process of finding faults in order to recover the things that what we have given, whether that has to be completed or not, whether we have achieved the desired results or not. Here, software testing, I can also explain it like that. Software testing is a combination of verification and validation. Verification means the things what we are doing, the process of doing or developing a system, is we are doing the rightly or not. And validation, that means what is the requirement, what we need exactly that I have received or not. What was the demand, what was the need, what was the requirement that we have need. That means we are going to validate the system by giving the inputs and verifying, with checking whether we have received the right results or not. So now going to the classification, here is a picture of the software testing, the combined. We have classified into the first broad categories, that is the unit testing, integration testing, and here is your system testing. These are the various levels of testing. Here we perform, in unit testing, we will perform black box testing, or we also called it as a functional testing. We also call the black box testing as a functional testing. Then we have a white box testing. It is also known as a structural testing. Got it? There are the different ways of performing the testing. In black box, we will use generally the two approaches: equivalence class partitioning or the boundary value analysis. In white box, there are the several other ways, like we will be using the fault base, or we are doing the statement coverage, branch coverage is there, condition coverage, or all the paths have been covered or not. Then the second level, in the second level, there is the integration testing. In integration testing, we will be doing the big bang methodology. Either we are integrating the systems, the small modules, the small units, we are integrating them. Then after integrating, there are the several approaches of integrating the modules, and several approaches we will be doing for the integration testing. Either go for the big bang, top down approach, or the bottom up, or we will do the mixed, or sometimes it has been also called it as a sandwich approach, where we have both top down and bottom up approach both. Then the system testing is there. Here we will perform all the testing, right? We will do all kind of testing there. That means we are combining the complete system as a whole. Look here, when firstly we have done with the unit, then we have done with the integration, then we have done with the system testing. And this system testing is combining all these kind of various testing. We will be doing the alpha testing, firstly the beta testing, acceptance, either regression testing, performance, volume, and the stress testing. They are the various kind of testing we will perform under the system testing. Now, the broad categories of doing the testing is your dynamic testing. Here, we also have one more categorization of testing, like we are having the dynamic testing or we have to do the static testing. So, the black box testing and the white box testing comes under your dynamic testing. Here, the functional testing, or we called it as a black box testing, or we called it as a behavioral testing. So, in the functional testing, in this approach, the test cases are designed using only the functional specification, using only the functional specifications of the software. That is, without the knowledge of internal structure of the software, that we don't know what is there in the inner part of the software. We only will be aware with the one interface, that from where we will give the inputs and we will expecting some outputs. So, what is the thing comes? The tester only knows the inputs, what kind of inputs has to be given to the system and what output what output should the system give out. It involves some observations of the output for certain input values. There is no attempt to analyze the code which produced the output. An approach to testing where program is considered as a black box because internal structure of the code is to be ignored. Here we are not worried about the internal structure. We will see the internal structure or the flow or the complete control flow or the structure in your white box testing, that we also called it as a structural testing. Here we will do the internal complete, where we will go for the path coverage, statement coverage, is there either all the conditions have been covered or not. So, here we have a focus only on what inputs can be given to the system and what output the system should give. What output the system should give and what inputs to be given to the system. So, in black box testing, the test cases are designed from an examination of the input and the output values only, and no knowledge of the design and the code is required here. Test cases, what is the term test case actually means? Test cases are the collection or a set of triplet. There we will have, say, one input, state and output, right? What we need? Inputs, the current state of the system, at what state your system is currently now, and the expected output. While giving to the system, what input if I am giving to a system, say add 3 numbers, that I am going to give the 3 numbers, right? And I will also know the what kind of output should be there. So, test case is a combination of these 3 triplets. Look at here, we are giving input. Now, the things come ki what kind of input we should give to the system. We will give the input according to the input domain. What is this input domain? That whatever the input we are giving to the system, it should be specifically from a specific set. Either what we have specified, say for example, if I am saying the day of a week, I have a specific domain like from Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. It is a set. Or I am saying give the, if I have to give the input as a some student name, the student name, what will be the domain? Input domain will be the some combination of the characters. If I say give the student number, there will be some specified series, specified numbers for the student number, right? So, there will be some specific input domain. I cannot randomly choose any kind of a input data for giving for the testing. So, we have to choose the data from the input domain only. So, we will give the input as data. Now, here is your system which is to be under for the test, and some output test data. I know what kind of output should be there, right? Here it will come the output test data, and it is also from some output domain. I know that if I am going to give you that I am inserting, say I am inserting 5. Say let us take an example. If I am inserting the value of the day as a 5, I know corresponding output what will be there, 5. That means Sunday, Monday, Tuesday, Wednesday, Thursday. That means output domain will be your Thursday. If I am giving 2, then the output, what will be the output? It will be Monday. The output domain is also fixed and your input domain is also fixed. Now, whatever the input we are giving, that will be also from the input domain, and output should also be there from the output domain. If it is not matching, then your system will fail. Then it will give some other kind of output. Look at here. Here is a system given, like say it is a input test data, complete data I am giving. Some inputs causing the anomalous behavior will be here. We have given it to the system. Now, some inputs which can create some problem, that we have also given. Here some output test results are there if we are having a correct input data. Then some output is also there, and these output will reveal the presence of the defects. It's not necessary that we have given the inputs causing the anomalous behavior. Some inputs can be, we have given the inputs from the domain, but the processing is like there that some kind of error, some kind of defects will be there. So there will be the some set of outputs, they may reveal the defects. Here, now for doing so, for doing the functional and the black box testing, we will be using several approaches. Those are equivalence value analysis, boundary value analysis, then equivalence class portioning, and the cause effect graphing. In today's lecture, I am going to cover these two, boundary value analysis and equivalence class portioning, and these two topics are very important from exam point of view also. Test cases that are close to the boundary, value have a higher chance of detecting an error. Boundary value, I hope you all understand. Say if I am giving the value of character should be between, say between C to M, right? So C is a boundary and M is a boundary. Say if I am saying, or I will say very precisely in terms of integers, if I am saying the value is between 1 and 100, what is the boundary? 1 is a boundary and 100 is a boundary. It has been seen the higher chances of detecting the error is at the boundary. Here what we have to do, boundary conditions, and input value may be on the boundary or just below the boundary, right? Or just above the boundary. That means below the boundary, if I am having some boundary, say up to 100, and below the boundary, that is of the upper side. Then just above the boundary, that means from lower side. So if I am having 1 to 100, from the lower it is 1 to 100. So 1 say just above, that is 2, and 100 say just below, that is 99. We have to check for all these kind of values. So what happens actually, programmer fail to see the spatial processing which has been required for these kind of input values that lie at the boundary, right? And of the different equivalence classes. Say let us take an example, say programmer may improperly use less than or instead of less than or equal. So what happened? If I will be using only this symbol, that means it is not including that number. If I am writing here A is less than B. Okay? Then what is happening? We are not including B here. If I am writing, that means I am including the B also. Conversely, less than or equal to for less than. It may be reverse. I need only, if I don't want to include the boundary, then I have to use this symbol only. If I have to include the boundary, then I have to use equal also. So the boundary value analysis leads to the selection of the test cases at the boundaries of the different equivalence classes. Like it has been explained with a very simple example. We have an input variable x with a range from 1 to 100, right? We have a value from 1 to 100. So the boundary value should be lower side, that means 1, right? And just above, it has been written here, just above the boundary, that means here, the lower side, that is 2. Then we will have your on the boundary, and just below the boundary on the upper side, below the boundary, that is 100. At the boundary, that what we will have, 1 and 100 will be there in the series of 1 and 100. What will we have? 1 and 100, right? But above and below, that we will include the 2 and 99 as well. We should select the test cases at the boundaries of different equivalence class if the input condition specifies a range bounded by the values A and B. The test cases should be designed with the value A and B and just above the A, right? If the boundary value is between the A and B, then the value will be with A and B and just above the A and just below the B. Here say again one example, say D is there with the input -3 and 10. Then what we will consider? -3 and 10. We will take it directly, that A and B. It is A and it is B. Then what we should see? Just above and just below. Just above -3, -2. And just below 9, and we will take in 0 as any nominal value between -3 to 10. It can be any nominal value. If an input condition specifies a number of values, test cases should exercise minimum and maximum numbers, and the value just above minimum and below maximum are also to be tested. Here we have taken an example as we have our two input variables, right? Say x and y. Now we are considering two input variables. So how we will specify the boundaries? Say one variable is x and one variable is y. The boundary of x is between A and B and the boundary of y is between C and D. Say the boundary of x is between A and B and the boundary of y between C and D. Then it has been seen both the intervals A and B and C and D. So for the input x, we may design the test cases like that. The value will be A and B just above the way and just below the B. Similarly for the y, like the value should be at C and D and just above the C and just below the D. So that these test cases will have more chances of detecting the error. We are doing the testing for detecting the error, right? For finding the error. So we should give the input of that type of input where the errors may come. The key points that we have to keep in mind for doing the boundary value analysis. The basic idea of boundary value analysis is to use the values at their minimum, just minimum, a nominal value just below their maximum and at their maximum. Now from this I can calculate the number of test cases, that minimum number of how many minimum number of test cases I can have. For a program of n variable, like if a particular program is having n variable, say x, y and z. So the boundary value, so the number of test cases will be there 4n plus 1. Suppose we have 3, say the value of n will be 3, got it? The value of n will be 3. Then what will be the test cases will be there? and 4n plus 1, right? 4n plus 1, that means we will be having 12 plus 1, that is around 13 test cases has to be required. Okay. Similarly, we have given the example. Suppose we have the two inputs, so we are having the values from 100 to 300. Likewise, we will design it 100, 100, right? 200, we are if having the test cases with the two inputs, say x and y, or the range of values will be 100, so between 100 to 300, right? So we have designed some test cases like that: 200, 100, 200, or 101. Like suppose here we have taken same, one is x and one is y. Got it? One is x and one is y. Here what we have chosen? One nominal value, the 100. Then the nominal value is 200, then 101. Nominal value is 200, nominal value is 200. Then nominal value is 200, then another, at the another place, 299 and 300. Now conversely, now what we will do? We will use the nominal value for the x, that is 200, and we will change the value of, we will fix the value of nominal value for y, and we will change the values for the x: 100, 101, 299 and 300. So this will give the some representation of the input domains and what for what values we have to test for the inputs, like from for x and y. Let us understand this boundary value analysis with one simple example. Like we are having for determining the nature of the roots of a quadratic equation, its input is a triple positive integers, like the value of n will be 3. Now here look at, the value of n will be 3. So the values may be the interval between 0 and 100. The value will be 0 and 100, and the program output will have one of the following output, right? The program output will be like this: not a quadratic equation, right? Real roots, imaginary roots, equal roots. So we have to design the boundary value test cases. This is the quadratic equation: ax square plus bx plus c is equal to 0. Roots are real if b square minus 4ac is greater than 0. Roots are imaginary if b square minus 4ac is less than 0. The imaginary and it is real. Equal if the b square minus 4ac is equal to 0. Equation is not quadratic if a is equal to 0. So these are the conditions, right? These are the outputs. When the real, when imaginary, when, so what will be the output? Output will be like, either it will give me the output like the domain real, imaginary, equal or not quadratic. We have taken 13 test cases. How? We have taken 13 test cases. The number of inputs will be A, B and C. That means 4 multiply 3 plus 1 is equal to 13. Okay. Right? We will have 13 test cases. Very simple. Now what we have started, the number of test cases we have designed, we are 3 inputs A, B and C, and this is your expected output. For A, 0, right? The values between 1 to 100. 0, we have checked it for 0, less than 0. Then 100. Then we have taken 50. Then 99 and 100. Just below and just above, right? From 0 to 100. Then again, for this what we have done, we have kept B as a 50, 50, 50 and 50, and the same for the 50, 50, 50 and 50. When we will keep put all these values in the quadratic equation, then we will got these expected outputs. Then again, now the values are here fixed. Now we will change the values of the B. That is 0, 1, 99 and 100. 50 is already covered here. This test case is already covered. So again and again we will not write 50. Okay. Then again, the A and C are fixed, then we will change the value 0, 1, 99 and 100. Okay. So we will get some expected outputs. So this is how you can create the boundary value test cases. Now there are some situations may also arise where the boundary values are not very clear. So in that situation we have to create our own boundary values. Say for example, in a process of employment application based on a person age, let us say from 0 to 12 do not hire, right? 12 to 18 may hire as an intern. 18 to 65 may hire as a full-time, and 65 to 100 do not hire. Look here, what we have seen, the age, this age, 12 is covering here, 12 is also included here, 18 is included here, 18 is also included here, 65 is included here and here also. Now, what we have seen, that means the ages will have two different classes. Like if the value will be 12, so there are the two classes. Either we should cap in a do not hire or may hire as an intern. Now for this, what we have to analyze, we will do some work, we will convert it here, and what we will see, the applicant age is greater than or equal to 0 and the applicant age is less than or equal to 12, we will say status is no, right? And again same, according to the situation we have converted into the if statements, applicant age is greater than or equal to 12 and the applicant age is less than or equal to 18, hire as an intern. If the applicant age is greater than 18 and the applicant age is less than or equal to 55, hire the status as a full. Then the applicant age is greater than 65 and the applicant age is less than or equal to 9, then hire the status as a no. Now, still the problem is there. The 12 is included here and here also, again the 18 is also included here, it is also included here. The same with the, it's not 55, it's 65, right? It is included here, 65, and it is also included here as a 65. Now what we should have, we have to keep these things 12 in one class, 18 in another class and 65 in another class. For this, we have to create our corrected boundaries and we have to standardly follow the same thing, like 0 to 11. That what we have done? We have reduced from the upper boundaries, right? Upper boundaries here it was 12, 18 and 65. So we have reduced it from the upper boundaries. You may do it, either you will reduce it from the lower boundaries. Here what we have done, I have reduced it from here, it's 11, now it's 18, it's now 64 and it's now 99. Uniformly I have reduced. Now what about the ages if the inputs are like this, -3 and 101. So the requirements do not specify how these values should be treated. So we have to specify if this kind of ages will be there, if this kind of input is also there, we have to give the specific output. Here again, now after the changes, the code will be implemented with the corrected rules. Now here it is 11, 17, 64 and 99. Now the boundary values for the test cases that we have to test for this example, like -1, 0, 1, 11, 12 and 13, 17, 18 and 19, 64, 65, 66 and 98, 99 and 100. Like how we are doing it? What we are doing? We are checking it for around 0, -1 and +1. Then we are also checking it for the 12. What we are checking it? -1 less, that is 11, 12 and 13. Then again I am testing for it 17, then 18 and 19. Then for here 65, 64, 65 and 66. And likewise for the 99, that is 98, 99 and 100. Here these are the now test cases and we will get our desired outputs. Second type of doing your functional testing is your equivalence class partitioning. How we will do this? Somehow it is also called it as a equivalent class partitioning. So in this approach, the domain of input values to a program is partitioned into the finite number of equivalence classes, right? so that if the program works correctly for a value, then it will also work correctly for all other values in that class. Say if I am saying, if I am delivering anything in a class, if I am saying one student is understanding, right? One student is understanding. If one student is saying yes, that I will assume that it will also understood by all other students. Or I will say, let us take it in another example. If I say, if the value of 2 is correct, if the value for the 3 is correct, the value for 4 is correct, I will assume the value for the 5 is also correct. So it will work like this. We have to divide the inputs into the classes, into the equivalence classes. So this partitioning is done such that the behavior of the program is similar for every input data belonging to the same equivalence class. The main idea behind defining the equivalence classes is that testing the code with any one value belong to the one equivalence class is as good as testing the software with another value belonging to that particular class. So equivalence classes for the software can be designed by examining the input data and the output data. How we will do this? Here are some general guidelines for designing the equivalence classes. Like, what we will do, if the input condition specifies a range, right? If the input condition is like some range, then what we will do, we will create the 3 equivalence classes, 1 valid and 2 invalid, right? Why 2 invalid? Because 1 valid, that means if I am saying 0 to 10, say example 0 to 10. So all the valid values from 0 to 10, and 2 invalid. That is, 1 is for the lower values from the 0 and 1 class is for the all the upper values of the 10. So we will have the 2 invalid classes. One valid class will contain from 0 to 10 and another class, one invalid class will contain from less than 0 values and the another will contain the values greater than 10. Then if the input conditions are the member set, definitely member set, so we will define only 2 classes, either from the member set and another from the another, right? Got it? If one from the member set, say I am having a set is there, say A, comma B, comma C, this is my valid, this is a set, right? This is my set, so I will create a valid class like A, comma B, comma C, and one invalid class will be M and O. Okay, like this. So the area, if the input condition is a boolean, so definitely boolean condition hai. If there is their boolean condition, then one valid, one invalid. Likewise, for the area code, the range value defined between the 10,000 and the 90,000, and the password is like the value. If we are talking about the range, if we are talking about the password value, it will be a 6 characters, like 6 character string that we are talking about a one set. So I will assume 6 character string in one set and non-string characters into the another set. It is that 2 steps have been required for implementing this method. What? The equivalence class are identified by taking input condition and partitioning it into the valid and invalid class. Like, if the input condition specifies the range value from 1 to 999, then the valid class will be, the item value will be 1 to 999, and the 2 invalid class, that is item is less than 1 and the item is greater than 999. Then second step is to generate the test cases using this equivalence classes identified in the previous step, and this is performed by writing the test cases covering all the valid equivalence classes, then the test cases written for each invalid equivalence classes also, so that the test contain more than one invalid class. Here the input domain will be containing the both things, valid inputs and the invalid inputs. So the system is under testing. We are doing the equivalence partitioning, and the output domain is there. The same. Some for invalid we will have some invalid outputs, and for valid we will have some valid outputs. So most of the time equivalence class testing defines classes of the input domain, and however the equivalence class should also define for the output domain. So we should design the equivalence classes based on input and the output domain. So how we should design? We should design the equivalence classes according to the based on input and the output domain. Here it is also again one example is have been 0 to value max and 1 is the valid, then input is less than 0 is invalid class, input max is less than invalid class. Let us understand this thing with one example that we have given. The range is 1 to 5000, right? We are doing the square root. So what we have identified? Invalid and one valid. So we will have a set of integers in the range 1 to 5000 and the integers larger than 5000 and the integers some negative integers also. Let's understand that particular example that we have also solved for the boundary value, finding the nature of the roots. So the output like we should have a equivalence class like the output domain, not a quadratic equation, real roots, imaginary roots and the equal roots. According to that, we have identified the test cases, right? 0, 1, 50, 50, 50, 50, 50, 50, 50, 50. What will be the outputs? Not a quadratic, real roots, imaginary and the equal roots, right? So we have identified the number test cases according to the output domain. Likewise, for the inputs. So how we have another set of input test cases based on the input domain, like if A is equal to 0, if A is less than 0, then the value of A will be between 1 and 100. The value of A is greater. Again, for the value of B is between 0 and 100 is less than or greater. Then what I have chosen only here A is equal to 0, not for the B. When the value of A is equal to 0, then we will find the another kind of a root. Then again for the C, the same, less than 0 and the greater than 0 and the value will be between the 0 and 100. Now according to this, we will create the test case here 1 to 10, and we will have previously we have the 4 test cases. Now what we have seen here, that this particular test case, this is repeating 50 and 50 and again. What we are doing now for A, B and C, getting me? For 8, A, B and C, what we are saying, we will be using any value that will be between 1 to 100. 0 to 100. Then we will be finding these 2 test cases are redundant. We will remove the redundant. We will use only one test case. So if we choose another value than the nominal, we may not have the redundant. Or I will use, instead of 50, 50, 50, I will change the value like 49, or I will write it is here 30. Then output will be the imaginary roots. Here what will be the another output, but we can change it. So the redundant test case will not be there. Now finally the total test cases will be 10 plus 4 for the output domain. So we will have total 14 test cases in this situation. This is how we can create the test cases manually, or how we will create the test cases with the help of the boundary value analysis and your equivalence class portioning. Thank you. That's all for today.